Alright, so I wanted to start this last day of notes, day 3 of Unit 7, with a couple more problems dealing with optimization. So you can see how it will look like on test day as far as the speed and whatnot. Alright, so here we go. The cylindrical container has a volume of 250. So we have a volume of 250 cubic centimeters. We know the volume formula is pi r squared h. This has to be memorized. It is from a cylinder. Okay? And if I were to solve for a variable, you're going to see in just a bit, I'm going to have to solve for h. I'm going to say 250 divided by pi r squared, because all I did was get h by itself. And you'll see why here in just a bit whenever we look at what we're trying to do in this problem. It says find the radius and height of the cylinder so that the surface area will be a minimum. Okay? So chances are I'm going to do a first derivative test, and that should be your first go-to. And if that doesn't work, you should know by now that you would do a candidates test. Okay, so let's first of all put in or find the equation that we're trying to minimize. So if the surface area, it's talking about, if it doesn't say specifically lateral surface area, in this case it's talking about surface area, it's meaning the whole thing, the total surface area. So we're going to minimize surface area. So I'm going to say the surface area is equal to 2 pi r h. It's going to be plus 2 pi r squared. Now you should see I have two variables. I have r's and I also have h, but I need one variable. Over here I'm going to substitute this 250 over pi r squared where you see the h. So then it's going to be s of r is 2 pi r, 250 over pi r squared, and then it'll be plus the 2 pi r squared. From here we should simplify it. Why not? Simplify what you have so that when you're deriving or when you're putting in the calculator, you're putting in less. So this will become an r on the bottom because it's simplified to a form of 1. So that we have 500 over r plus 2 pi r squared. Okay, this is s of r. So immediately I'm going to go to my calculator. Okay, let's clear the problem that we've done before. So menu 1, 4 to clear A to Z. This clears all the storage. And now menu 1, 5 to clear everything that we have. So we're going to look at this and we're going to find the critical points of s prime of r. Okay, so ultimately we're trying to find what are the critical points that would set this derivative equal to 0. Okay, so if I go over here and I go ahead and put the 500 over r, I'm going to go ahead and put fraction 500 over r, and then I'm going to end up adding the 2 pi r squared. So 2 pi r squared, and I'm going to save this as my s of r. So control store, it's going to save as s of r, and there it is. Now we're going to find the derivative. Now the work that I want you showing is the solve feature is the derivative in respect to r of s of r. When it's equal to 0, you must write this since you're going to be using your calculator so that r is approximately equal to whatever 6 decimal place value answer that we're going to get here in just a bit. So we'll say menu 3.1, we're going to do the solve feature. This button right next to the number 9, we're looking for the first derivative. My variable is r, and it's going to be s of r. Okay, so let's go over here, s of r, kick out once, set it equal to 0, comma r. And then you can close and control enter if you want. And you get 3 point, let's go up and get 6 decimal places. So 413920. So let's go ahead and write r is approximately 3.413920. We know that's here. And then what we're going to end up doing is doing a sign test of the derivative of said surface area. So coming up here, we'll say, first of all, control clear or control delete to clear this line. And then we'll say menu 4 for calculus, 2 for derivative at a point. And our input value is r. And again, back here, we want to solve for something like 3 and 4. Those are our test points because 3.4 lies in between. So we'll put 3 here, first derivative. We're going to test it. S of r, and then control enter, and we get a negative answer. Okay, doing it again, go up twice, grab it. This time we're going to put a 4, you're going to get a positive. So this shows you a minimum, which is exactly what we're looking for. Okay, so we don't have to do the candidates test. So we'd write per first derivative test, the surface area will be a minimum when, in this case, R that we found was, we'll go ahead and round it now, 414 centimeters. And if we were to subtract this, or not subtract it, but put it into this equation here to solve for h, and then round the answer of h to 3 decimal places, you should get 6.828 centimeters. And we say because S prime of R, changes signs from negative to positive. Okay? And there it is. That's the work. Okay, so now what we're going to do is we're going to do number 7. Number 7 says a rectangle is bounded by the x-axis and the parabola. So basically the rectangle looks like that. Okay? And the y value, basically the function that you see here, is an inverted or reflected across the x-axis parabola shifted 4 units up. That's this guy. So that'll give you any y value depending upon where its x value is located. It says what length and width should the rectangle have so that its area is a maximum. So we're trying to maximize area. Oops. So if we're trying to maximize area, we have to come up with an equation for area. That is base times height. Now our base over here, since we said that this is xy, that means this x value, oops, let me choose a different color, means this x value represents this right here. Okay, so if I'm looking at this rectangle right now, I'm going to say the base is 2 times x. Okay, so it's basically 2 of what you see right now, because it's going to be to the left of the y-axis, symmetrical wise. So there's your base, and your height is going to be this y value. So it's 4 minus x squared. That's any given height, and it's variegated throughout the problem. That means it's changing. It's not going to be a constant height. As you can see, the shape of this rectangle would be different, like if it was here at this point to here at this point. It would be something like that. So on and so forth. It's changing. That's why we're going to leave it as a variable. Okay, next one. I'd probably do here, since this is subtracted, is distribute so that I get 8x minus 2x squared, or sorry, 2x cubed. This is my area. So that I get a of x is equal to 8x minus 2x cubed. So that my a prime of x is negative 6x squared plus 8. Solving this out the way we've been doing, 0 is equal to negative 6x squared plus 8. So that 6x squared is equal to 8. Okay? By now you should see the answer is going to be this plus or minus square root of 4 or 8 over 6. So x squared is equal to 8 over 6. This is 4/3. Taking the square root, x would be the plus or minus because of the fact that I've square rooted both sides. We have a plus or minus answer. Alright, so x is going to be plus or minus 1.154, whoops, yeah, 154,701 units. Now let's see where we got that at in regards to what work we're going to show. So the first thing that I want you to think about is, let's put in, this equation in our stored memory. So I'm showing you that you can do some of it by hand, and some of these you will actually have to solve it out. Obviously we can't get the decimal here, but we could have something like this. So let's go ahead and put it into the calculator right now. So menu 1.4 to clear the storage. Menu 1.5, this helps prevent all those falses and trues that you're getting, that some of you are mixing up, either mixing up the variables or you're not clearing out your storage. Okay, so we'll say parentheses 2x times parentheses 4 minus x squared. And this is going to be stored in as a of x. Okay, so control store, we'll call it a of x. Oops, syntax error. I need to put parentheses around my variable. Okay, so now that it's saved, now I can start doing the first derivative test. That's my first go-to. Okay, so what is it that I'm about to do? I'm about to do this work with a calculator by making it say solve the derivative in respect to x of a of x when it's equal to 0, comma x. Okay, I must show this work. And this x that I find should yield this value here. So let's go ahead and look for it. Here we go. So to be menu 3(1), it is the derivative. My variable is x, and I have it stored as a of x. Okay? Oops, messed up with the parentheses there. So let me go back. A of x. Kick out once, equal to 0, comma x. And then I will close it, control enter, and you see the plus or minus. If you want to get those 6 decimals, just go ahead and go up there and grab them like that. So we have 701 because it's a rounded answer. And again, you can round or truncate. But notice that I did 6 decimal places as I'm going through the problem. So it should be 701. I see what I did. Someone probably would have sent me an email in that regards trying to get those 3 points, but I caught it. Okay, so 6 decimal places. And all I'm going to do is quickly, especially those of you who might be struggling still, is I have negative 1.155-ish and positive 1.155-ish. I'm trying to test 3 intervals. So it looks like the first interval is probably going to look like a negative 2. 0 is a good one for the middle one, and then 2 for the last one. I'm just testing signs where these would lie. Okay, so let's go ahead and write the work down. I'm going to do the derivative with respect to x of a of x line x is equal to negative 2. We'll see what this is equal to. And then we'll do the derivative of a of x line x is equal to 0. And this line will come into play whenever we start doing integrals. I just want you to get a little bit familiar with it right now. A of x line, and this is when x is equal to 2. And then we'll see what sign that gives us. So real quick, let's go over here. We'll control clear this, and then we'll menu 4(2) so that we can get the derivative at a point. My variable is x. The first one that I'm looking for is negative 2. And I am going to look for the first derivative. What I'm going to put there is a of x. Okay, not just a, you need the input variable and function notation. Some of you are struggling with that in regards to inputting it into the calculator during class. I do get a negative answer. Okay, so I'm going to go back here, and I'm just going to do is equal to a negative. Okay, that's all I care about. I'm going to go back up, and I'm going to try 0 now, because that's my second test point. And when I do that, I get a positive answer. I have a positive here, so equals a positive. And then the last one, I'm going to test it at 2. So let me go up twice, and then I will get 2, and it gives me a negative. So negative, positive, negative. So negative, positive, negative. Okay. Now, what I want to do is the maximum area will occur right here. Okay. And we're going to say, we're going to write it out. Let's go ahead and write it out so you can see again the time that it's taking to do this. We're going to say per first derivative test. Okay. So per first derivative test, a maximum area occurs when say the width is 2x. So when width equals 2x, which in this case, it's going to be 2 times this number of 1.15, so on and so forth. Okay? So multiplying this number to 6 digits, like 701154. Okay, so 1.1547001 multiplied by 2, we get an answer of 2.309. Okay, so 2.309. 2.309 rounded right now because it is my answer. We'll put units. It's not asking inches or anything in particular, so we'll have to make sure we write units. The length is going to be the 4 minus x part. And putting that in the calculator, it should yield an answer of 2.667 units. Okay? And then we're going to say because a prime of x changes signs from positive to negative. And that's it. That's the work showing that example. Now let's go ahead and go to the notes that we have. Okay. Alright, so the last part is linear approximation and differentials. Two small little things that will finish up this unit. Okay? And they really don't relate to what we've done so far. They feel like they're a little bit disconnected, but the differentials kind of tie in here and there, and you'll understand more how when we do the integral part starting next unit. Okay, so let's go ahead and begin. It says the tangent line to a curve gives a useful way to approximate the value on a curve. When I say the value, I'm talking about like at a specific y value, an output. We usually write our tangent line equations like this. We've learned it from Algebra 1. Okay? And what we've done recently is we've graduated to where y1 is now f of a, or f of x, and the slope is f prime evaluated at a. Everything else is pretty much the same thing. So when we are using tangent lines to find the approximation, basically what we're doing is we're rearranging this to this, so that the linearization, and it's sometimes written as the linearization of x is equal to so on and so forth. So you could put, if you want, L just all by itself is equal to all this stuff here. If you want, you'll see it like that sometimes in textbooks and whatnot, but you can leave it as y, just like you see it in your notes right here, boxed in. You can leave it like that because it's meaning the same thing. Okay. So it says, note, y represents the y coordinate, okay? And it depends on a. So it's basically saying, what would the y coordinate be if my x value was this particular value here that I have highlighted? This gives us an approximation. It's an approximation from a tangent. Some of you might be thinking, whoa, 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 whoa. I thought the instantaneous exact was tangent, and that approximation was secant. Okay, if you're talking about slopes, you're exactly right. But what it is that I'm saying it gives an approximation of a y value, not a slope. Okay, this equation right here, which we've been doing, equation of a tangent line, just rearranged, gives an approximation of the y value evaluated at a. This is that same y value that we're talking about here. Not an approximation of a slope, approximation of a y value. So the y coordinate of a on the function f of x is represented by f of a, and we call this, f of a is the actual value. So here in just a bit, with this first example, what's going on? Write the equation of the tangent line of f at x is equal to 1. So if I'm going to do the equation of a tangent line, I know that it's going to be y minus y1, like I could use this if I wanted to, equals m times x minus x1. My at value of x is equal to 1 is going to go here. Okay? What I need to do is I need to first find a slope. So I'm given the function that when I derive it, I get 2x. So I need a slope, otherwise known as f prime evaluated at this 1. And I need an actual point. So that means like x, y, otherwise x, f of x. Okay? So my x value is 1. So f of 1 means put this value into my original, so my output is 1. But if I put this value now into the derivative function, I can get the slope right here evaluated at 1, which is 2. So all this is going to happen is, it's going to be y minus 1, that's that y1 value, is equal to the slope times x minus the x1 value, which is this other one. And you can leave it like this if you want, because this is the answer. Or you can simplify this out, move some stuff around, and put it in y-intercept form. Either of these would work. Okay? Now part B says, use your answer in part A to find the approximation of this guy. It's basically saying, if I choose, I'm going to go ahead and use this point slope, or sorry, y-intercept form. Let's say that I assign my equation as this, from what I got from part A. It's saying f of x is equal to 2x minus 1, of course. So if I'm trying to find f of 1.01, all it is plugging it in. F of 1.01 is 2 times 1.01 minus 1. My output y value is 1.020. Okay? And this is an approximation. Okay? Now part C says find the actual. So if I were to find the actual, it's basically saying don't use the approximation that you got from the tangent line that you got from part A. Remember, that yields an approximation that we said over here of a y value. It says use the actual value. So we're not going to put 1.01 into this equation that we found. We're going to put 1.01 into the actual function that we had originally. So the actual would be f of 1.01 is, well, x squared, 1.01 squared. So that f of 1.01 is 1.0201. Okay? So I'm just showing you to 4 decimal places of how close this would be away from the approximation. So this is the actual or the exact. Okay, this is the actual or the exact, whereas comparatively over here, this approximation. So we're 1/10,000th of a point off. Okay, so it was just 1.020 versus 1.0201. So they're really, really close. Okay, you'll learn these approximations in BC calculus or in Calc 2 when you go to college, but for now just know that they're one's representing finding the approximation, but it still yields a very, very almost exact answer because the error is very, very minimal. So it's basically saying it's off by 1/10,000th of a point. So we're going to say the error is off by, so it says find the amount of error of your approximation. So let me write that out so that you see what it looks like. It will be the error is off by, we'll say 1.0201 minus 1.020 is equal to 0.0001. Okay? And this is, you could put units if you want, and you'll say approximate under the exact. Okay? So the approximation is under or less than, we'll write approximation is under the exact. And that would be your answer for part D. Alright, so now let's go to another example. Use the tangent line to approximate the value of the cube root of 127. To do this, let the function equal the following, and then choose the perfect cube close to 127 so that you can build your tangent line. Okay? So first of all, we know the function that we were given is the cubed root of x, which if you wanted to rewrite it would be x to the 1/3. Okay? So now what we're going to do is we're going to, first of all, we need to derive, because we know we're going to use the derivative because of that tangent line that we're going to be doing. So power rule says 1/3 x to the negative 1/3, sorry, negative 2/3, which is going to be rewritten as 1/3 x to the 2/3. Now it's been a while since we've done this part, but this is our derivative here. Okay? I have no negative powers nor square roots in the denominator. We know that our tangent line, of course, comes from y minus y1, mx minus x1, otherwise known as f of a, just like you saw on the last slide. f prime of a, x minus a. A is our at value. Okay? And now, linearization, you just get y by itself because you're trying to approximate it. I know it means the same thing and you're just like manipulating by moving stuff around, but I just wanted to make sure that you are familiar with this equation textbook-wise. Alright, so if I come over here and I start working the same example with my cube root of 127, this is how I'll start. F of a is equal to the cube root of a. Therefore, f prime of a is equal to 1 over 3, a to the 2/3. We already know that. We're going to say let a equal 125. So f of 125 is equal to the cube root of 125, which is simply going to be 5. Okay? So what is it that we just did? Well, we obtained an a value and a y value. So basically, this is my input x value, and this is my output y value. Okay? So what am I going to do with this? Well, if I put the y value over here where the y value goes, I'm going to have y is equal to 5 plus, I need to find what this is as far as f prime of a. Because ultimately, yes, it's going to be x minus 125. Okay? And that 125 came from here, the x value of my point. So far, all I've done is use the point, the y value, and the x value, the x at value. So now I just need to find the derivative and then plug in that slope, whatever it is. Okay, so the derivative is over here, and if I plug in my at value, and again, my at value is the x, I'm going to put 125 right there. Okay, that is my x at value. Okay, so 1 over 3 to the 2/3, so I'm going to come over here, and I'll say 1 over 3, parentheses, and my x value is 125. And it's going to be raised to the power of 2/3. And when I control enter that, I have this weird decimal answer as far as 0.0, whoops, I see what I did wrong. I need to, real quick, do the second cubed, and then it is 3. Let me go back a little bit. It is 1/3 x to the 2/3. I'm going to make sure I did this correct in order to get the slope. And I'm putting in my at value. My at value is something close. So I put in, I put in 125. Okay, yeah, so I was right. So from the calculator, the f prime of x, or the f prime of a, we put 125 as our a value. We took the derivative function and we plugged it in. We got 0.0133. Looks like it's repeating, and it is. So 0.013, 0.013333. So 1, 2, 3, 4, 5, 6. Okay. Now what we're going to do is we're going to approximate, because remember, we chose 125. Okay, let a equal 125 because we wanted to find a perfect cube that was close to 127. Because again, we're approximating based off of something that is close to an exact answer. So we know 125 cube root is 5. That's an exact answer. And we chose that because ultimately we're going to get this approximated answer for this cube root of 125. Something very, very close to it. We wouldn't choose something like 6 cubed, because 6 cubed is way, way too far away. So if we chose 6 cubed, alright, 6 cubed is 216. It's too far away. If we chose 4 cubed, it's not as close to where it could be. That's 64. We wanted something as close to 127 as possible, so we chose 125. Alright, so what is it that we're going to do with this? Well, now that I have my linearization, or tangent line approximation, if you will, I can plug in the 127 right here. Okay? So 127 minus 125 is going to end up as 2. So it's basically like 5 plus 0.013333, and it's going to be multiplied with 2. This will give me my approximate y value. So let's go ahead and put that in the calculator. So we will multiply that answer that we had way up here by 2, so times 2, and then we'll add 5 to that. So that 5.027. 5.027. This is the approximate answer. And we're going to compare it to what is the actual. So let's keep going to as far as writing out. So we have 5.0266666. So it's what 3 more 6s. I'm just trying to show you the exact how close it is as far as answer. So 5.02666. So 0.26666. That's where that's coming from. And the actual answer would be, what is the actual cube root of 127? We're not using the tangent line. We're going straight to what is the cube root of 127. Okay? So let's go ahead and put 127 raised to the power of 1/3. This answer would be right here. So we get 5.026, 526. 0.26, 526. This is the actual. So 5.026, 526. So if I wanted to see how off we would be, you could then again say the approximation in this case is going to be over, because this one is 0.26666. This is 0.26, 526. So we'll say the approximation is under the exact by, and we could do it simply by subtracting. Hold on, not under, probably people are pouncing and ready to send me an email, is over. The approximation is over the exact by, and we're going to put the answer there as far as what we're going to get. So it's 5.0266666 minus the 5.026, 526. Let's go ahead and put that in the calculator real quick. So we have 5.026, 123, minus the 5.026, 56, or 526, not 56, 526. And the answer is 0.00014. So it's very, very minuscule as far as how off it is. Okay, I know things are written to 3 decimal places, but for the sake of these errors and just for these errors, I'm reminded that I do want you to write as exact as you can. So if it doesn't tell writing up to 6 decimal places, by all means do so. The only thing that I will tell you here is there's really not a, okay, write it to 6 decimal places or you're wrong. On this instance, because if I wrote it to 3 decimal places, I would have 0. I want you to at least write it to 4 decimal places. If you feel comfortable just copying what you see, just copy what you see. So you say that it's over approximation by 0.00014. 0.00014. Now, when you're under approximation or over approximation, this is always going to be a positive. Okay? This under or over will tell you whether or not it was a negative or a positive as far as the way you're going to interpret it. But the actual number, like 0.0014, I want it to be a positive. Okay, that's like whenever we're saying from related rates, decreasing at a negative rate or decreasing at a positive rate. Okay, so whenever you're saying this, it's always going to be positive as far as your number. That negative or positive interpretation will come from whether you put over or whether you put an under approximation. Notice that this number is still positive. Okay, so we're going to go over here and we're now going to look at our, let's see, last part says, from calculus, Leibniz, so the German used the notation dy dx to represent the derivative If you don't know by now, I'm not sure if I've covered this in class. Not extremely important, but Leibniz or Newton, there's a fact of who got the credit for discovering calculus. We'll talk about that maybe sometime in class, but for right now, there were two mathematicians as far as it came up with calculus, just in slightly different ways as far as what variables they represented for f prime of x or y prime and all that. dy dx, if you did not know it, came from the German Leibniz, and he notated the derivative of y in respect to x as this dy dx. Okay? No, that's not a test question, just a little FY, little math trivia. All right, so the notation looks like a quotient of real numbers. So it looks like it's being divided, but it is really a limit of quotients. This is what it truly is, in which both the numerator and denominator go to 0. We already know this. Without actually equaling 0, because you can't divide by 0. Leibniz did most of his calculus using dy and dx as separate entities though. But he never quite settled the issue of what they were. So to him, he called them infinitesimals. So these infinitesimals, or non-zero numbers, basically were these infinite smalls. Okay? It's tricky to define dy dx as separate entities, but since we really do not need to define dy dx as formal variables, the textbook defined them in terms of each other. And that's why we have the quotient dy dx. Okay, so let's go to the definition. I have a function. It is differentiable. Means that I can take the derivative all throughout the domain. And the differential d of x is independent variable. So is the input variable. And the differential dy is the f prime of x basically the output differential. Okay? And how did I get from this to this? Well, I simply I simply took the derivatives in respect to each other. So, implicit differentiation. If I'm going to derive y in respect to y, well then it's just y prime. Or in this case, just dy. Again, we're talking about these infinitesimals. Okay? So, looking at f of x, it's f prime of x, so the chain rule, multiplied by the derivative of the cream, or the derivative of the inside, which is dx. Okay? And again, they're seemed as separate entities is what we're trying to define right now. The variable dy is always the dependent, and depends on both x and dx. Okay, so let's see what this is entailing as far as examples. Find the differential dy and given the function. So we know if we just treated this as a normal derivative, it would be the derivative in respect to x is equal to 15x squared. Okay, so if I try to move things around, even though this is truly not dividing that's occurring there, it's the derivative of the limits, I can interpret this as, okay, if it is division happening there, and I wanted to basically move things around, I could look at this as, well, how can I get rid of this dx? Well, I can multiply, and again, this is not really truly multiplying, you're just manipulation as far as moving it around. And again, you'll discover this more in depth of what it means when we do the integral part. So dy is equal to 15x squared dx. So it says, find the differential dy. It means basically get dy by itself. No dx in the denominator. Normally derive this with respect to x, and then move things around so that you can get this differential, this infinitesimal all by itself of dy. And that would be your answer here. dy is equal to 15x squared dx. Pretty straightforward, pretty simple. Again, you'll understand more when we do the integration part. The radius r of a circle increases from 10 to 10.1 meters. Use the differential d of a to estimate the increase. So it looks like it's going to be increasing in the circle's area. Okay, so first of all, area is pi r squared. And again, this is my input variable of r, and my output looks like it's going to be a. So if I take the differential, it's basically going to be in respect to r. So it'll be dA dr, and then over here it's just going to be the regular derivative. 2 pi r And that's it. Because dr implicit differentiation wise, it's just going to be 1. So it's just going to be 1, so we don't have to necessarily write it. It's in respect to r. Okay, so getting it by itself, we do like we did on the last example. We could interpret it as multiplication, even though truly that's not what's happening. dA is equal to 2 pi r dr. So now that I know that, I can plug in values that I have. Okay, so first of all, the radius that we had was 10, and it's 2 pi, and it's dA. Well, what is that differential piece? What was that small, subtle change? Well, it's basically the error. It's the change in that r. So if I changed from this to that, the change was a positive 0.1. So it would be a positive 0.1 that would be multiplied in the place of dr. Multiplying this out with the calculator, I'd get approximately, rounded to 3 decimal places, 6.283 meters squared. This is the estimate. How do we know it's the estimate? Because it is based upon the differential that we're looking at. Okay, the differentials, the infinitesimals. Okay. Now, the first area, if I were to try this and actually manually do this, I could have, the first area is, again, pi r squared. It'll be pi times 10 to the squared, so it's 100 pi, which is about 314.159. However, if I look at the, again, these are exact over here, because we're going to measure as far as how they're different. So pi r squared, this time it's pi 10.1, and it would give me an answer of 320.474 meters squared. So subtracting that 320.474 minus the 314.159 is going to give me a 6.315 meters squared. This is the actual, rounded to 3 decimal places. Okay, that was the actual increase. So the actual increased by amount of 6.315. Whereas over here, we're saying the estimated increase was about a 6.283. So if we compare the estimate with the true change, what would be the error? We would say the error is hold on, let me come over here. The error is the approximate is under we would say the approximate is under the exact. Now I realize what I'm writing. It's an under approximation. Okay, so we're going to say the estimate, or I'm right. The approximate or estimate answer is an under approximation of the exact. So I could just write it just like approximate is under the exact. Okay, or you could just say it's an under approximation by a certain amount of things. So I could say error is an under, just different ways to write it. Approximation of, or compared to exact. Compared to exact. And we would simply do that by, or find it by 315 minus 6.283, and we get the under approximation is by that. So we could say the error is an under approximation compared to the exact. Okay? So, or you could write it like this: the error is the approximate is under the exact by how much? I don't want you to get confused about how to write this out. So maybe just the boxed way that I'm showing you right here would be best. The approximate answer that we got way up here is under the exact that we got over here as far as 6.315. By how much? We'll say by about 0.031 meters squared. Alright, so enough of that. Now let's go to our last example, and then I believe we are done. It says the following. It says, suppose the Earth were a perfect sphere, and we determined the following. The radius to be that, and what effect would the tolerance of this be as far as the estimate of the Earth's? Ooh, I might have cut this off. Hold on just a bit. Yeah, I'm sorry. I'm just realizing that this is not the one that I wanted to give. This is not the example that I wanted to give. So we will scratch this off. This will not be on the test. Okay. So that's it. That's all you have for the notes. I would say something to think about in regards to how to prepare for this linearization and this differentials, again, is to look over the supplemental homework. Okay, so the supplemental homework in groups and whatnot, you have plenty of time. Now that we know our test won't be until after the 3-day weekend, please by all means look at some stuff and work it out as far as relating it to the video and how we did certain things. Alright,